In this video, we're going to be talking about absolute extrema. This is a pretty cool idea because it builds very nicely off of some of the discussions we've been having with regards to just maxes and mins, right? So I'd like to preface this video though with a little question, and that is the following. Are the mins and maxes we've been finding so far the largest and smallest points on the graph, right? So you might remember we found min values using our first and second derivative test, and same thing for maxes, things that look like that. We could find max, min, yada yada yada, but we never really stopped to consider if those were in fact the smallest or largest points on the graph everywhere, right? We knew that there were some kind of max or min, but we just didn't know if they were the smallest or largest everywhere, right? So in this video, we're going to sort of dig into that just a little bit and see if we can come up with some cool ideas, okay? All right, so let's look at this little function I've got for you guys here, right? So I'd like you to take a second here and find me the extreme values. And just looking at, we can just do this looking at the graph, right? Well, we have a max over here, right? And we have a min over here. Pretty straightforward. You could, if I asked you to, take the first derivative of that, find your critical points, and use a first or second derivative test to tell me exactly where these values occur. But we don't worry about that. We're not worried about that at this point of time, right? So here's my question. I'm going to throw that question back at you again now. So I'm going to throw back this question here, which is, are these the largest and smallest points of the graph? Take a second and see if we can figure that out. Well, let's talk through this then. So what's happening over here, right? So this max right here takes a certain pretty high y value, right? But there are much higher y values here on the function, right? There are much higher y values up here and here. And actually there's going to be infinitely many y values that are bigger than that, right? Because this function goes up towards positive infinity, there's just going to be infinitely many numbers bigger than that, right? Same thing, same idea can be applied for this minimum here. So that minimum takes a y value like right about over there. But as you can see, the function has so many more y values down here that are smaller than that, right? So these things are much smaller than that minimum there. And there's going to be infinitely many y values that are also smaller than that minimum because this function is going down to negative infinity down there, right? So the answer to this question is actually just going to be no. The max and the min are not the biggest and smallest points on this graph, right? So that leads us to leads us to ask the question, like, is there any concept of having a largest or smallest point on a graph, right? So because clearly we're not able to do that with our current vocabulary, so we're going to need a few more additional tools to do that. And that's where absolute maxes and mins, or absolute extrema, come into play. Right, so let's go over some terminology really quickly before we start knocking some problems. So the first thing is that so far all the max and mins we've been calculating so far have been what we call relative, right? Another word that's thrown around there is local. Both of these are interchangeable for the purposes of this problem, but basically what this is saying is that if you look at this graph, that max right there may not be the biggest point everywhere, as we just discussed on this graph. It may not be the biggest point everywhere on this graph, but it's still big within this reason. It's still the biggest within like a reasonable region, right? It's the biggest point for a general area. And same is true for the min. It's the smallest point given a general area. So the concept of a relative or a local extreme value means that it applies to a general area. Right? So yeah, that's basically how relative maxes and mins work. Now let's talk about what absolute extrema do. Okay, so absolute extreme values are going to be the largest or smallest y values that a function takes on. So as opposed to my relative maximum, my absolute maximum will be the largest point anywhere on this graph, right? My absolute maximum will be the largest point, no questions asked, anywhere on the graph. Same thing goes for my absolute minimum. Unlike my relative minimum, it's going to be the largest point anywhere it's going to be the smallest point, anywhere on this graph, right? So that's the idea of an absolute extreme value. It's the biggest, the smallest. Okay. Now you might have noticed I used a very interesting choice of vocabulary here, and that I used the word y value. Now that's very deliberate, right? And that's for the simple reason that an absolute minimax can occur at multiple x values. Now you might think, given our vocabulary, that this, like, if I have a function, right, that takes on a certain highest y value multiple times, that might not actually be the absolute max, because if we think of the absolute max as just the biggest point on the graph, then it doesn't make sense to call that the absolute max if there's multiple if that value occurs in multiple places. However, however, our vocabulary, right, for that we use in math allows us to say that an absolute max or min can occur at multiple x values. So that would be okay with the situation we just talked about. So we had a function which went like this, for example, right, which had like a highest y value like this that occurred at multiple x values, and a really small value that occurred at multiple x values. Those are still going to be my absolute min, and that's still going to be my absolute max. So it's totally fine to have the absolute max value occur at multiple x values, right? And that's the whole reason we use that terminology. Okay. Now, how do we actually find these? Now, here I'm going to go through some steps with you guys, and we're going to actually work on one of these problems together and sort of piece together everything through that, right? So let f of x be x cubed minus 3x, a very similar little guide to what we worked with just before. And so what we're going to do is we're going to find the global extrema for f of x on the interval -2, 2. Now, this is the most common type of problem you're going to see, where you're given this kind of closed interval. Now, the reason that works, right, is because if you remember back to this graph, there is actually no like absolute max or absolute min, because, right, this goes up to positive infinity, and this goes down to negative infinity. So there's no one biggest or smallest value. However, what we can do, right, is if we're given this kind of interval, we can lock off the function to this interval, right, -2 and 2, and we can just say, let's just focus on this interval and see what's the biggest and the smallest value on this interval, right? And then we can use that and make that our absolute max or min. And that's the most common type of problem you're going to see. There's lots of other types of absolute extreme value problems that there's a lot of other types of absolute extrema problems that you might see, but this is the most common one. Okay, so let's talk through it. The first thing we're going to do is we're going to find our relative extrema, because these are still the most still very likely candidates for where our absolute extrema could also occur, right? So we're going to go through the same. I'm going to go through this a little bit faster just because we've done this process many times before. But basically what we're going to do is we're going to find our first derivative, right? Which is, in this case, going to be 3x minus 3, just using a power rule, 3x squared minus 3, excuse me, using a power rule. And we're setting that equal to 0. And we will get that x squared equals, if we push the 3 over there, divide by 3, it's going to be 1. So x is going to be equal to plus or minus 1, right? So that's the first part of that. Now the second part of this is we're going to use, I'm actually going to go ahead and use a second derivative test. Yeah, just because it's a little bit easier because it's a polynomial, so generally those are a little bit easier to do a second derivative test on. A first does also work though, just don't forget that. So f double prime of x is going to be it's just going to be 6x. So f double prime of 1 is going to be 6, which is greater than 0. So we have a min there, right? We also know that f double prime of -1 is going to be -6, which is less than 0. So we're going to have a max there. Cool. So we have our absolute extrema down, our relative extrema down, excuse me. The second step to this will be to also look at what we call endpoints, right? So the reason we look at endpoints is because if you look at what's what's going on in this graph, for example, right? Where could the biggest or smallest values of our function occur, right? Well, they could occur at the extreme values, like our relative extrema, but they could also occur at the very ends of our interval, right? So you could have one over there, you could have one up here, for example, where we sort of cut off, where our interval sort of cuts us off, right? So we could potentially have extreme value, the biggest or smallest value of the function occur over there. So that's also something that we are going to investigate. So here's what we're going to do now. So we want to find it, we want to get our endpoints, right? And in this case, our endpoints are just going to be x equals 2 and minus 2, okay? And then what we're going to do is we're going to test all of these, all of the points that we have as our candidates, right? So how we're going to do this is we're going to basically draw a little chart right here, right? We're going to have x and f of x, and we're going to plug in each of these, our potential candidates, which are going to be these and these. We're going to plug these into f of x and find which one is the biggest value, the biggest value, right? And or the smallest value, and we're going to use that to judge absolute extrema. Okay, so let's start with x equals minus 1, right? So f of minus 1 is simply going to be minus 1 cubed minus 3 times minus 1, which is going to be the result of minus 1 minus, so this is minus 1 minus minus 3, so that's going to be a plus 2, right? So we have, that's going to be, so we have that. What about minus 2? So we're going to have f of minus 2 is going to be minus 2 cubed minus 3 times minus 2, which is going to be, that's going to be negative 8. That's plus 6, so this entire thing is going to be a plus 6. So this is going to be a minus 2. Let's try positive 1 this time. So f of, running out of space here, so I'm just going all over the place. So f of 1 is going to be 1 cubed minus 3 times 1, which is just going to come out to 1 minus, no, that's going to be a minus 2. Yeah. And then last but not least, we would have 2 itself, right? So I did that. F of 2 is going to be it's going to be 2 cubed minus 3 times 2, which is 8 minus 6, which is just going to be 2 again. Okay. So now the biggest y value in all this is going to be our absolute max, and the smallest is going to be our absolute min. The smallest y value here is minus 2, right? That's your smallest y value, and it occurs at 2x values. So this is going to be our absolute min. Let's maybe use a different color just to distinguish here. And this right here is going to be our absolute max. And as we mentioned before, it's perfectly fine that these occur at multiple x values. Okay, that's totally fine. Right? So that's the process of how we calculate absolute maxes and mins. This is I hope you understood the idea of how, firstly, what absolute extrema are relative to relative extrema, and then how to actually go about this process, right? So that's that for this video. If you found this video helpful, please do like, share, subscribe, leave a comment, and check out some other videos. See you next time!